My name is Divine, and today I'll be presenting on WTCL-Dehaze, Rethinking Real-World Image Dehazing via Wavelet Transform and Contrastive Learning. And my advisors are Donghai, Guan, and Mingqiang. For today's presentation, we'll be going through the context of the introduction, literature review, our proposed approach, conclusion, and future work. Now, before we go in, we would like to explore what image dehazing is and what are some of the challenges that are faced with hazy images. Image dehazing refers to the process of removing haze from images taken from outdoor environments. And this is crucial for many applications such as autonomous driving, surveillance, and remote sensoring, where image clarity directly impacts the performance. Hazy images are typically characterized by three issues. Number one, we have the color distortion. Number two, we have low light, low contrast, and loss of details. And one of the most common way we can model this problem is through the atmospheric scattering model, which is formulated as Ix is equal to Jx Tx plus A 1 minus Tx. Now in simpler terms, the first term, Jx Tx, represents the light from the scene passing through the atmosphere. And the second term, A 1 minus Tx, represents the light that is scattered by the haze. This challenge in recovering dehazing image is quite difficult because we have to recover Jx, the clear image, from Ix, the hazy image. And so now this is an ill-posed problem because we have to estimate both Tx and A without directly having access to them. Some traditional methods have attempted to solve this problem, but they often struggle to generalize across different environments. And this is where our learning-based approaches come in. Now we would like to look into some literature review on this work. For the literature review, we can characterize them into 4 parts. We have the prior-based methods, the learning-based methods, semi-supervised based methods, and the transformer-based methods. For prior-based methods such as dark channel prior and color attenuation, these methods usually rely on the statistical properties of clear images. These methods work well in some conditions, but however, they struggle in complex scenes with bright regions like the sky in the image. Learning-based images, including multi-scale CNN and GAN-based approaches, use deep learning to directly depict or generate clean images. While these methods can be effective, they require large amounts of labeled data, which can be difficult to obtain, especially for the real-world images. For semi-supervised learning-based methods, some works have emerged, such as Wang and Chen. They demonstrate how leveraging both synthetic datasets and unlabeled real-world images can improve the model's generalization. However, this approach is the one we actually used in our work. That is the semi-supervised methods. We also have the transformer-based methods, such as the Dehaze former, which was published in 2022. They use transformers to capture the global context, which is very useful for image dehazing tasks, but these methods are very computationally expensive. So our goal here in our work is to overcome some of these limitations by combining elements from these existing methods with some innovations. Now we would like to look at our proposed approach for our work. WTCL-Dehaze introduces a semi-supervised learning framework that leverages both wavelet transforms and contrastive learning. This model was designed to handle challenges of real-world images as well as synthetic images, particularly in situations where we can't find clean images. This is so because some of the real-world images, most of the real-world images don't have clean images, so we'll have to use semi-supervised to make it work better. Now, by combining the strengths of the wavelet transform, which has the multi-scale analysis, and contrastive learning for better feature extraction, our model generalizes well with both synthetic and real-world datasets. Now we'd like to look at some of our components in our work, in our architecture. So at the very core of our model, we have the discrete wavelet transform. And this discrete wavelet transform allows us to decompose our input image into 4 subbands, which are the LL, the LH, HL, and HH. For the LL, which is the low frequency, it represents the low frequency component or the smooth areas of the image, which captures the overall structure. For LH, it focuses on the horizontal details, while the HL captures vertical details, and HH extracts the high frequency textures and the fine details. Now, the advantage of using the discrete wavelet transform in our work is that it provides the multi-scale feature extraction and allows our model to generalize well with both global structures and fine details, which are very crucial for the image dehazing task. Next, we would like to look at another key component of our work, which is the contrastive learning. The contrastive learning plays an important role in distinguishing between hazy and clean images. We use the contrastive loss to train our model to bring dehazed images closer to the clean images, while pushing it away from the hazy image in the feature space. And this is how it works. In our model, the positive pairs consist of dehazed images and its corresponding clear image. And negative pairs consist of hazy images and their dehazed image. So by training the model in this way, we ensure that the feature representation of our dehazed images become closer to the clearer images, improving the overall quality of our dehazed output. Now we'd like to look at our architecture. So for WTCL-Dehaze, we design our architecture to handle complex tasks, ensuring that the important details of the image is well preserved. In doing that, we have components like the skip connection, which we can see throughout our networks. In the skip connection, we use it to transfer spatial information directly from the encoder to the decoder. And these connections help the network to retain crucial details that would otherwise be lost during the downsampling and upsampling process during training. We also have the residual layers. Our work uses the residual layers to accelerate the training and also improve the output quality. The residual layers allow our model to learn residual mappings, making it easier for our network to converge during training and enhance the clarity of our final dehazed image. Now, unlike other methods, our model does not use batch normalization. And this is intentional because introducing batch normalization might produce unwanted artifacts during the image restoration process, especially when dealing with fine details. So to avoid that, we remove batch normalization to ensure that the image's fine textures remain intact. In our work, we also use DWT and IWT, DWT being the discrete wavelet transform and IWT being the inverse wavelet transform. And in our architecture, we use the discrete wavelet transform in the encoder. We use it to break down the input image into multiple frequency subbands, which allows our model to focus on both global structures and fine details. We also use the IWT, which is the inverse wavelet transform, in the decoder, and this reconstructs the image from these four subbands, combining the learned features and the high quality dehazed image. Our model also uses the semi-supervised learning method, as we stated in the existing methods. And this allows us to train both labeled synthetic data sets and unlabeled real-world images simultaneously. This enables our model to generalize better across diverse hazy conditions and make it effective in real-world applications. Now I would like to look at some of the evaluation of our model. So in our work, we evaluate our model using two key matrices, which is the PSNR and the SSIM. We realize that our model outperforms the state-of-the-art methods, achieving a 1.97 point increase in PSNR and 0.079 improvement in SSIM on the SOTS dataset in comparison with the semi-dehazing paper, which is a TIP paper published in 2020. Our model also has the performance of PSNR increased by 2.88 in PSNR and SSIM by 0.029 for the HSTS dataset. And over here we have some metrics for our ablation study, and with L here being the number of loss functions that we used. We firstly used the baseline and the loss functions. We realized that there was an increase in our model, but as we kept adding other details, it kept getting better. For example, we can see that there is our baseline plus the loss function and DWT and IWT, which has 26.8 and 0.029 9.2. And with our contrastive loss as well, without the DWT and IWT, we have a performance of 26.56. But with the combined details using the loss functions, the DWT, IWT, and contrastive loss, we can see that our model achieves a better performance in our ablation study. For the data sets that we used for our work, we used the SOTS and HSTS, which are both synthetic data sets, and we also used real-world images to ensure that our model generalizes beyond synthetic data sets. And we tested them on various real-world hazy images as well to validate its robustness. Here are some of the images that we obtained from our training. This is from the synthetic dataset. This is the HSTS dataset, to be precise, and this is from the real-world images. Now, when we look at our synthetic data set, from the images that we produced, these are the hazy images, and this is the ground truth, being it the clean images. As we can see, both qualitatively and quantitatively, our method achieves a better result and is the image closest to the ground truth, which is using the color, the texture, and also the contrast. This also applies to our real-world images. We realize that this is the hazy image, and with ours, it has less haze, and this is the main purpose of our task, to remove haze from the images. Now we go to conclusion and future work. So in conclusion, the WTCL-Dehaze represents a significant advancement in image dehazing, outperforming existing tasks through the combination of wavelet transform and contrastive learning. And by using our semi-supervised framework, we improved our model's generalization across real-world conditions. And in the future, to improve our work, we would like to integrate transformer architectures to further enhance the global feature extraction, and also to extend our work to other challenging tasks such as low-light image enhancement and underwater restoration. So thank you very much for your attention.